Hello, everybody. Welcome to today's TinyML Talks. My name is Danilo Pau, and I have the great pleasure to introduce you today talks of Gian Marco Iodice, tech lead in ARM Machine Learning Group ARM. The title of his speech will be Unpacking the Music Genre Recognition Project from the TinyML Cookbook, second edition. Before to leave the floor to Gian Marco, let me remind that this episode of TinyML Talks, as well as many other events organized by the TinyML Foundation, are possible thanks to the support of our TinyML strategic partners. Let me remind them one by one. AIZip, Arduino, ARM, BrainChip, Edge Impulse, Embed UR, Efficient, Greenwaves, Grovity, IMAX, ImageBob, Infineon, Inatera, Nota AI, NXP, PNG, PIMIC, Polling Technology, Corvo, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, ST Microelectronics, Synaptics, Syntian, TDK. As you can see, the list is growing from time to time, and this is a strong sign of support we receive from our partners. It's of paramount importance to be a community, as you well know, in particular part of the TinyML community. And this means two things. First of all, meetup. Be part of the meetup. The meetup are organized by many groups, quite 50. In 41 countries, and the membership, the number of members are growing, and the LinkedIn TinyML community, which is rich of members. In both ways, you can contribute, learn, exchange, network with others, and this is one of the fundamental added value of being part of the TinyML community. There is much content you can learn from the TinyML YouTube channel, an incredible amount of videos and contents on many subjects which are covered by the TinyML, hardware, software, tools, applications, and much more. And so you have an incredible freedom to pick up the content, the subject you want to deep into. And this is all available, and is a great result of the content made available by the different members of the community and contributors. Register now to attend to the flagship event of the TinyML community, the summit, which will be held in San Francisco, April 22 to 24. There will be also the symposium co-located with the summit. Is the capital letters event in which learn from different experts in the TinyML community. There will be an incredible amount of contributions, and therefore you cannot miss this event. So register now and stay updated on the TinyML website for the latest news. Apply to the awards. The awards in TinyML for this year are about the best product, the best prototype, and the Sustainable Future Pioneer Award. So these awards are very important. Apply on them, and also don't miss the opportunity to see who will be the winner, which usually is declared during the summit. The community and the foundation produced the 2023 AGI Technology Report, which is an important guide for all the freshmen, young engineers who would like to understand more what's going on the AGI technology. And a new version is under preparation and will be released soon, likely in April or so. So let me introduce quickly Gian Marco Iodice. Gian Marco is an experienced edge mobile computing specialist at ARM for machine learning. He's also chair of the global meetups for the TinyML Foundation since 2022. He received the MSc with honors in electronic engineering from the University of Pisa in Italy, where he specialized in hardware software co-design for embedded systems. Within ARM, he leads the engineering development for generative AI, a quite strong topics, and the ARM Compute Library, which he co-created in 2017 to run ML workload as efficient as possible on ARM Cortex-A CPU and ARM Mali GPUs. In 2023, he collaborated with the University of Cambridge to integrate machine learning functionality on the ARM Cortex-M microcontroller powered by Algae. Still, in 2023, Gian Marco contributed to developing the EdTech for Good Curation framework. This framework, developed by UNICEF in collaboration with ARM and Asian Development Bank, represents a significant step forward in the responsible use of technology in education, which is great to learn. Thanks, Gian Marco, for your availability and to stay with us today. And I need to.
So thanks a lot, Danilo, for this introduction. It's actually my pleasure to be here and have the opportunity to talk about the second edition of the TinyML Cookbook. I'm excited because, yes, I have the opportunity to talk about a bit more about the book, but in particular about a couple of chapters of this book that I believe are quite relevant to many machine learning developers. The project that we're going to unpack today is about the recognition of music genres. This looks a classification problem. It is a classification problem, but what we're going to discuss today will be mainly about the pre-processing. So the important role of crafting, designing the pre-processing for the target device. But let's start step by step. And first of all, I want to thank you all, because if there is the second edition, it's because of the first edition and incredible support I have received in the last year from the TinyML Foundation, from ARM, and many developers that contact me also on LinkedIn to include new chapters and new projects in this book. This book is an incremental edition, so it's not a completely new book, which means that you can find some of the projects created for the first edition, but there are more. So there are other additional projects as well. So in particular, the new projects featured in this edition are the music genre recognition. So in the area of audio sensor with TinyML, there is a project with object detection using the formal technology with edge impulse. Quite very interesting, because these showcases the object detection capability of microcontrollers. Plus, well, I probably have seen at the very end, or at the very bottom of this slide, the backpropagation of microcontrollers. In other words, on-device learning and scikit-learn, because these are two hot topics at the moment in the TinyML world. On-device learning promises very important new features or new capabilities to these devices. And scikit-learn is another important project, another framework for TinyML, in addition to TensorFlow Lite for microcontrollers that we will discuss today. So there is also a new companion for this book, because the first edition was mainly built around the Arduino Nano 33BLE Sense and the Raspberry Pi Pico. But this edition also features an additional board, which is the SparkFun Redboard Artemis Nano. So you have 3 different platforms to experiment and to these TinyML projects. Before I move on, because I think I forgot it, so there is a giveaway session. So in order to enter this free giveaway session, where I'm gonna give away 5 free ebooks copies, you just need to attend this presentation. You don't need to do anything apart from maybe interacting, but this is not mandatory. You just need to attend, and we're gonna take your contact, your email, and if you're gonna win, you're gonna be contacted directly by email. So I think, well, this is probably the most important question that I want to address from the very beginning. Where can I find the code presented in the book, but also presented today? Well, on GitHub. On GitHub, you can find the code is under a permissive MIT license. Each chapter has its own folder with a summary of the project and the with the Arduino source code, the Colab notebooks, the Python scripts. And also in each chapter, there is a shopping list, because this is a very practical book. So in some cases, you won't need any platforms, but in most of the projects developed in the book, you will need hardware, you will need cables, you will need sensors, and this is actually the beauty of TinyML, right? So you have this board, and you can experiment, and you can bring to life actual and real applications. So concerning the chapter we're gonna unpack today, and given the limited time, we're gonna address in particular one aspect of chapter 5 and chapter 6. We are here. The book has been structured to have a Gaussian learning experience. So, so we are more or less in the middle, where the difficulty goes to the peak. This means that you need to be to a solid embedded programming skills, and you have a very solid machine learning. After chapter 6, basically you start going down in terms of difficulties, because you expect you are you have a very solid understanding of these two topics, and you're gonna go to the end, where you're gonna see on-device learning on microcontrollers, in particular on the Raspberry Pi, Pico, Arduino Nano, and SparkFun Redboard Artemis Nano. So what you will learn in the book and what you will learn today. So here there is a list of things you're gonna learn in particular in the book. So since the Raspberry Pi Pico, which is the target device for this chapter, does not have a microphone, you're gonna learn how to connect an external microphone to the microcontroller. You're gonna also record audio samples with the microcontrollers with the help of the ADC peripheral. So you're gonna learn also how to sample the signal and produce audio clips that automatically will be uploaded to Google Drive. This will be very handy, because since you're gonna train your models in a Google notebook, having all these samples in Google Drive will be very, very simple to basically build the training data set. Yes, once we have collected data, we will build the data set for music genre recognition, and we will delve into the implementation of the feature extraction. We're going to discuss in particular today the Mel-frequency cepstral coefficients with TensorFlow. And we're going to also discuss how we can implement with the help of CMSIS-DSP library in Python. Yes, you read it right, Python. Here, I'm not talking about just C, also in Python. And this is probably the most important feature for TinyML developers, and we're going to cover it today. There are other things we're going to learn in the book that we won't address today. For instance, the design and training of the LSTM recurrent neural network, which is supported in TensorFlow Lite for microcontrollers, the evaluation of the accuracy of the model, and the implementation of the MFCC algorithm in C and the final application. Just to make it clear what we are going to address today, in green, I have reported the areas we're going to discuss in this talk. So what you will need the Raspberry Pi Pico. For the book, there is optional use of the SparkFun Redboard Artemis Nano, which means that in theory, you can also reproduce this project on this board. You need the solderless breadboard in order to plug the Raspberry Pi and connect the microphone with the auto amplification. What else? Well, apart from your laptop, Google Drive account, and Google account for accessing Colab, nothing else. So why this project? And it's quite interesting, because everything started 12 years ago. That was a project I built to learn actually the basics of embedded programming. I was at uni and I wanted to develop an MP3 player from scratch using C. And trust me, 12 years ago, it wasn't like it is right now with the plethora of libraries we have for microcontrollers. Also Arduino, well, there was Arduino, but certainly we didn't have all the libraries that we're seeing now. But I want to see one thing just for okay, so about this app, because actually from this app I have learned most of the optimization we're going to discuss today. But what you can see that 12 years ago we were already capable to run sophisticated algorithms. We're not going to discuss these algorithms today, but the reason I decided this project is because when I built the MP3 player, one of the features I was interested in having in this project was actually the auto-equalization. So recognizing the music genre and adjusting the bass and the trebles to have the best listening experience. But at that time, it was a quite challenging task to have ML on board, and now it's actually very, very simple. But as you can see, there is also the user interface, which is quite smooth, as you can probably see. But one of the questions you might have in mind is, well, how is possible this interface can be so responsive and smooth, since there is a screen overlay, anti-aliasing effects, which are generally computationally very expensive. But there are no tricks, because or no hardware, specific hardware, dedicated hardware acceleration. Here, I only use the ARM Cortex-M CPU in this particular case. And the tricks were two, actually. Perform the computation only when strictly necessary. And the second aspect is about trying to pre-compute as much as I can the computation that is repeated, okay? And store these values in flash. Because the flash is usually the portion of a memory, is usually larger than the SRAM, and we can certainly put data there to speed up the computation. These two tricks were actually behind the user interface that you have seen before. And the program memory and the CPU are actually the two ingredients that made this user interface quite smooth. The soft optimizations applying in that project have been actually adopted for this for the project we're going to see today, in particular for the extraction of the MFCC. So when we talk about TinyML, well, this is generally speaking the view of TinyML. Well, this is the simplistic view because actually is more complex than that. And if we see what is the complex view of TinyML, well, there are at least three other blocks that we need. The data collection that sometimes could be not as simple as we think. And the other aspect is the design of the feature extraction, which, well, the feature extraction is quite crucial for TinyML because although we might consider, and there are cases where the feature extraction is part of the learning problem, for TinyML, there are still cases where the feature extraction must be dedicated also outside the model in order to keep the model quite compact. Remember that here we have a very limited RAM availability and also flash availability. So by designing a feature extraction, we also generally increase the chance to have a smaller machine learning model. But designing a feature extractor is quite simple in Python, but it could be quite challenging in C. And in this project, I have proposed a way to actually make this process less painful. And we're going to see later. So the additional ingredients to this complex view of TinyML are, as I said, the data collection, that in order to have a robust model, we should collect the data using a target device that we aim to use in a real-world scenario. There is another aspect, which is about the selection of the suitable ML input data. Well, I talk about music genre recognition, but the question here is about, well, how long should be the sample for my model? Well, this cannot be completely a random choice. This is dictated by the target device. By knowing the target device, we can have the answer to this question. But the target device is also the center of the implementation of the feature extraction in Python that needs to match numerically what we're going to have in C in order to minimize the risk of accuracy drop. So data collection, well, our application needs a microphone to record the songs and classify the music genre. Since the Raspberry Pi does not have a microphone, we have to use one. And for the book, I have opted for the one electrode microphone, which returns an analog signal, but it also has the MAX 9814 amplifier, which is it auto adjusts the signal amplitude based on background noise, for instance. The reason for opting for this microphone compared to other options, because now there are also digital microphones as well. It was because I also wanted to explain how to use the ADC peripheral on Raspberry Pi Pico. So it was mainly behind that. Of course, if you want to have better microphone or signals in terms of with reduced noise, there are also other alternatives that you might consider. But that is the main reason. And in the book, there are the steps that will bring you to connect the microphone to the Raspberry Pi Pico. There are only a few wires needed, as you can see on the right-hand side. There is also a push button attached to the attached to the Raspberry Pi Pico in order to record the song. This is basically to help us to collect the data that we upload to Google Drive. So every time we push the push button, the Raspberry Pi records the song through with the microphone, and with a Python script, we send the data to the Google Drive. And so, yes, I have briefly described actually the what it happens here. Right here, I have in short written what I have described verbally just a few seconds ago. So in the book, there is an implementation of the Arduino Sketch to sample the audio signal with the ADC peripheral. These samples are with a frequency of 22 kilohertz and transmitted over the serial communication. So the Python script has been implemented to grab these samples, generate the audio samples, and transmit these samples to Google Drive in order to be accessed in Google Notebook. In Google Notebook, we have we used Google Notebook to train the model. So, and the audio clips are recorded every time the user presses the push button. This is quite handy because since you might need to record different songs for recognizing the music genres, that in this particular case are only 3, but you can extend it to as many music genres as you want. It is quite, as I said, it's quite handy, and it's quite quick to record everything and having everything in Google Drive. So, in terms of the data set, so the data set contains audio clips recorded with the Raspberry Pi Pico. In particular, with the Raspberry Pi Pico, we record 4 seconds of audio every time we press the push button. In the book, I suggested to record at least 10 audio clips per music genre, but the more, the better. In order to have a larger data set, I also recommend to use the GTZan dataset, which is actually a good one for music genres because it contains 10 different music genres: the blue, classical, country, disco, hip hop, jazz, and so on. For each genre, you have 100 audio clips that are 30 seconds long. Of course, both GTZan and the audio clips recorded with Raspberry Pi Pico should have the same frequency should be, the frequency, the sample rate should be the same in order to simplify and avoid any artifacts in the songs, and should have also the same as sample weight, which is 16-bit in both cases. I believe you have probably started to do some math already. So I talk about 30 seconds per clip for GTZan. I talk about 4 seconds for the audio clips recorded with Raspberry Pi Pico. How much memory do we need for these clips? Well, it's quite impractical to consider both 30 seconds and 4 seconds. And if you do a bit of math, consider 16-bit of data with a sample rate of 22 kilohertz, you discover that you need 1 megabyte for 30 seconds and 176 kilobytes for the 4 seconds audio clips. So both are impractical. We don't have enough SRAM. We only have 264. So as a result, we decided, well, to consider shorter audio clips of 1 second long. And this choice certainly helps us to reduce the memory required to 44 kilobytes, because you have every second you have 22 kilohertz, but since we have 16-bit data type, you need to multiply by 2, and we have this value. So in order to get this 1 second, we take all the audio clips and we split these clips in chunks of 1 second. We haven't overlapped these chunks, but you might consider also overlapping these chunks to have also a very big data set, which is not strictly required for the task we aim to solve today. But I believe you also have a question in mind about, well, is 1 second model input length enough for our problem? Well, if you consider, for instance, a disco song, you probably realize that 1 second is not enough, because usually a disco song is a mixture of genres, right? So yes, there is a disco music, but sometimes they like to mix and match other genres, right? So 1 second is, I would say, probably not enough. However, it doesn't mean that from only 1 second we need to predict the music genre for the entire song, because we can take a song, we can split in chunks of 1 second, and for each chunk we can perform the ML inference, and we can average the results, and at the end we can say, well, this is probably a disco music or a metal or a jazz music. So that is the way of thinking. So how the targeting, as you can see, the target device influences our strategy to solve the problem. Is not the other way around. Feature extraction, and probably here we are going to spend a bit more time, because this is the crucial part of the chapter, and probably where I spend most of the pages to describe this algorithm. Why? Because when we think about TinyML, we think that ML is the only problem that we need to solve. Not at all. So the pre-processing plays a crucial role in TinyML. If we have a pre-processing, we have a very high probability to make also the model smaller. But we need to consider the complexity to implement the pre-processing. And today, with the next few slides, I'm gonna address this aspect. So first of all, let's not reinvent the wheel. So we know that from many acoustic models, handcrafted engineering input features like the MFCC is quite good. And it's quite good also for music genre recognition. So let's start from there. So we have 1 second audio clip. Let's extract the MFCC and let's perform the machine learning model inference. The pre-processing generally is a stage that prepares the data, the raw data, to be good for the machine learning model, but also to reduce the amount of data at the same time. I like to see this step as a compression plus an adjustment of the values in order to work quite well for the machine learning model. So you need to have both in order to make it working, in short. So the algorithm or the stages actually involved in the extraction of the MFCC are described in this image. So you have your input audio, which is 1 second long, and this algorithm defines a set of frames of frame length overlap with a distance of frame steps. So you have different windows, okay, on this audio signal, and for each window you perform the sequence of operation you can see here. So you perform the hand window, the FFT, the magnitude, the Mel scale conversion, the logarithm, the DST, and the extraction of the MFCC, which are basically a set of the DST output. These frames are generally overlapped, okay? So and these overlapping is basically defined with a frame step. As you can guess, this algorithm depends on some hyperparameters, and we need to know the algorithm in order to play with this hyperparameter. Well, certainly we can put random values, but probably it takes longer to identify the suitable values for our problem. That is the reason we probably need to spend a bit of time to understand the algorithm in order to have the best bet on the hyperparameters of this algorithm. Here there is a frame length, so we need to decide how long we want to make each window when we extract the MFCC from the audio signal, because these coefficients are extracted from each window. So you have a sort of image we're going to see later. The other aspect we need to play with is the distance between two consecutive windows, which is the frame step. The FFT length, which is usually also equal to the frame length. So how do we decide this value? We will see in a bit. The Mel spectrogram attributes. This is related to the Mel's conversion. And we're going to see also this aspect today. And the number of MFCC to extract. Well, if you're not familiar with the algorithm, well, say, well, I trust you. So I have no idea what these values are. So let's unpack all of them, and let's see basically how we can determine these values, or how we can guess the right attributes for this algorithm. So first of all, we have an FFT, and if you are digital signal processing experts, we know that we need to apply a filter in the time domain before applying the FFT to minimize the spectral leakage. And usually for this kind of algorithm, we apply the hand window. And this is the formula that we apply. What can we infer from this formula? That is not computational. It is quite expensive in terms of it is quite computationally expensive. Well, it's quite simple because there is a cosine to perform. There are also a bunch of multiplications involved and divisions as well. But if we pay attention to this formula, we can also notice that there are some coefficients here that can be pre-computed. So, of course, it all depends on how we can, let's say, how we can store these coefficients, the data type of these coefficients. But let's keep in mind this aspect, because from this formula, we can infer that actually the argument or the parameters of the coefficient of the coefficients of the window can be pre-computed, and in order to improve the performance. So it's a very simple operation, but quite expensive. The operation that follows the window is actually the fast Fourier transform. This is a real fast Fourier transform, as we usually refer, because the input data is a real data. And since you have a real signal, you have the frequency as symmetric to the positive. So to the positive one. So you have the spectrum, which is quite is symmetric. And here we can probably also figure out what is the best frame length or FFT length, because the distance between two consecutive frequency is the frequency resolution. And this frequency resolution depends on the input frame length. So, which means that if shorter the frame length, the lower the frequency resolution. But for application like ours, where we know very good, we want to keep the spectral details in order to capture the pitch, harmonics. Usually the frame length should be around 90 milliseconds, 100 milliseconds, okay? So in order to grab or to have a very a decent frequency resolution and grab all the details that we need. After the FFT magnitude, we need to after the fast Fourier transform, we need to perform the magnitude, which is actually a complex magnitude, because after the fast Fourier transform, we have a complex values. And the FFT magnitude is required to have an understanding of the energy distribution, because it gives us the relevance of each frequency component. So if some components have very large, very big values for the FFT magnitude, it means they are quite relevant for that class or for that signal. And now we enter the interesting domain of the Mel scale. So far we have talked about FFT, so we talk about the Hertz scale. But because of the necessity also to compress the data, there is an interesting scale which has been inspired by the human auditory system. The Mel scale I like to define as a type of compression technique, because it reduces the number of frequencies. And the way it reduces the number of frequencies is by applying a logarithm transformation to the FFT frequencies. To apply this conversion or this frequency conversion, you must define the boundaries of this range, so the Fmin and Fmax. So the Fmin, this is the lower frequency on the Mel scale, and the Fmax, which is the higher frequency and cannot be higher than the Nyquist frequency, for instance. And of course, we need to define the number of Mel frequencies that generally is smaller than the frequency that we have on the Hertz scale. So given the nature of this transformation, as I told you, is a logarithm transformation, we can also infer that we can use a fewer Mel frequencies, because many lower Mel frequency correspond to the same Hertz frequency. And this will be quite clear probably with this image. You can also find in the book. At the top, you can see the Mel frequencies, which are all placed equidistant. But when we apply the transformation to bring them back to the Hertz scale, you can notice that the distance between these frequency becomes larger and larger and larger with the increase of increase of the Mel scale with the Mel value. So, and that is the reason we usually have also fewer Mel frequencies than FFT frequencies. But okay, quite interesting. But how we can apply this transformation from the Mel scale to FFT? Because first of all, we don't have the exact match between the Mel frequency and the Hertz frequency, and also we don't want to lose the contribution of some FFT frequencies. And the trick here is quite simple. We apply a set of triangular filters, and these filters are placed for each Mel frequency, as you can see at the top of this image, and are equally spaced. And as you can see on the Hertz scale, these triangles are actually, they have a different, I mean, the base is quite different. It's not always the same, right? Because of the logarithm transformation. But this filter is used as to group the frequency, the FFT frequencies, and give a weight to each of them that contributes to that particular ML scale. So in short, this is a weighted filter where you apply a weight of 1 to the FFT frequency that contributes more, and you apply 0 to the frequency that contributes less. But how, from this description, how can we perform this transformation? This is just a vector by matrix operation. And since this transformation is the same for all the windows, it also means that this is constant and can be pre-computed. So we have identified another aspect of the computation that can be pre-computed and saved. The DST part is the last part of this algorithm, and here I have reported the scary formula behind it. But if you look at the formula, you can notice exactly the same thing I had mentioned earlier. This is just a vector by matrix operation, which means, and since this is the same applied for all the windows, it is constant and can be recomputed as well. This is the third aspect of the computation that can be pre-computed to save clock cycles and improve the efficiency of this algorithm. Before we move on to the actual implementation, I want to make just one note about the MFCC, because if you're using Python, you have different options. And in our case, we have used TensorFlow. However, TensorFlow is not the only option, because you can use also librosa, or you can use also, there are also other libraries out there. And for instance, on GitHub, I have reported an example to extract this with librosa. However, you need to keep in mind what you're going to deploy on the Tiger platform, because what you use in Python for training your model must match numerically what you're going to have when deploying the model on the actual device. As you can see at the bottom, they differ, but not because one is less accurate than the other, simply because the underlying implementation can be different. Can be different in terms of coefficients used for the hand window, for instance, or it can be different from any other reasons. The important thing, and here I want to stress this aspect because it can save time, remember what you're going to use for deploying your model, because in Python, you have a plethora of options, but when you deploy in C, you might not have the same plethora of options that you have with Python. And the implementation in Python and C must match numerical to avoid any accuracy loss. Okay, quite interesting. I talk about this algorithm. This algorithm is generally implemented in floating point. However, we need to keep in mind the Tiger platform. And the Raspberry Pi Pico does not have a floating point hardware acceleration, which means that all the floating point operations are software emulated. In other words, it's not very efficient. Well, this doesn't mean that we cannot have a better implementation, because one of the ideas to improve the performance of this algorithm is through the fixed point arithmetic. In other words, exploiting integer arithmetic. So if we have, as you have seen previously, for accelerating this algorithm, we need an element-wise multiplication for the hand window. We need the FFT, we need the complex magnitude and vector by matrix. Well, this fixed point story is quite compelling, but interesting idea, but how can I implement in Python and C? So because there's a lot of effort implementing this. Well, if you're targeting an ARM-based microcontroller, like the Raspberry Pi Pico, well, implementing this algorithm can be quite simple and efficient using the functions available in the CMSIS-DSP library. On a collection of C functions, and here you can find exactly the function I have described earlier. You can find mathematical functions, metric functions, domain transformations, and so on. So, as I said, exactly what we need. But this is not everything, because although we have the C functions, what makes this library quite useful is the fact that it provides also the Python library that match with the same functions that match the numerical precision of what we have in C. Furthermore, what we write in Python is very, very close to the final implementation of the microcontroller. I'm not going to the details on how to write this algorithm. Of course, if you're curious, you can explore the code on GitHub or read a book. So there is a detailed explanation in the book about the fixed point arithmetic, how it works, and implementation. But I reported a snapshot of the Python implementation and the C implementation for the MFCC. And as you can see, the syntax is very, very similar between the Python and C. And this is actually quite good, because if we need to bring this algorithm to C, it means that the effort at the same time is not that big, because the API is quite the same. There will be some differences because of the nature of the two programming languages, but certainly it's very, very similar. So, this is the implementation and that we have implemented. So at the top, the MFCC implementation that is translated to the following building blocks you can see in the light blue. So the hand window with the element-wise operation, the FFT with the FFT, the magnitude with the complex magnitude, the Mel scale we have learned that is just a vector by matrix. The logarithm, this is the only operation I haven't discussed earlier, but well, if you're using Q15 or the fixed point arithmetic, we have a limited number of possible values, right? Therefore, why don't we pre-compute also these values in order to speed up the computation? And that is the default, actually, default optimization that we have applied for this algorithm. And in the end, we have the DST, which is implemented, again, with a vector by matrix operation. But I guess now what you want to discover, well, I need to pre-compute quite a lot of stuff here, but how much memory do I need to pre-compute all these data? So these values are stored in Flash because they're constant, so no SRAM consumption at all. There is 153 kilobytes to store all these buffers, which means only 8% of the total program memory available. The program memory is another best friend for you, because all the constant data should go there in order to free the SRAM, in order to leave the to give flexibility to your algorithm to store temporary data in SRAM. But what is crucial is that this Q15 implementation is certainly non-numerical accurate to the floating point one. However, the fact that we are going to train our model with this data type, and this data type is exactly what we are going to deploy on the target platform, will reduce or minimize the risk of accuracy drop when deploying the model. So we're approaching the end of this talk. So, and as I said, I'm not going through the other recipes of this chapter, but in the book you will find the recipes to design and train the LSTM recurrent neural network, which is implemented using the many-to-one structure, which is a classic one for classification tasks. Here I have reported the model that we have that has been proposed for music genre recognition. It has a 15 kilobytes of trainable parameters, and accuracy evaluated in the floating point domain is around 90%. And since you are all expert of TinyML, you also know that floating point is not the best. We need to quantize to 8-bit using the TensorFlow Lite converter if you're using TensorFlow. And using this conversion, this tool, we can reduce the model size to we can bring the model size to 23.5 kilobytes and preserve the accuracy, because we haven't experimented accuracy drop, which is still around 90%. In the book also, there is an evaluation of the accuracy of this quantized model, the implementation of the MFCC feature extraction in C, in the Arduino IDE, and in the end, the application development for recognizing the three music genres, which are disco, jazz, and metal. Before we leave, I think one interesting aspect of this project and many other projects presenting the book is around the Arduino TFLine micro library. So unfortunately, an official pre-built Arduino TFLine micro library that support all Arduino microcontrollers is not available. As a solution for the book, and is also available on GitHub, we have included a pre-built TFLine macro. So this library should work with any Arduino compatible platform. And for this, I need to give credit to Pete Wood because actually it's based on his project for building the TFLine macro Arduino library for the Arduino Nano 33 BLE Sense. So in short, I have removed all the references to the Arduino Nano 33 BLE Sense in order to make it compatible for a wide range of Arduino platforms. For those eager to know the necessary tweaks that you need to make to the Arduino TFLine macro library, there is a notebook called a notebook on GitHub to generate your Arduino TFLine micro library. And we're approaching the end of this talk, and I hope you found interesting. I want to leave you with three things. So first of all, TinyML is unique. It's unique because what you build, you also see immediately its impact in the real world. But it's also unique because this is a field where you need to know the hardware, what hardware and software needs to be together and must know each other at best. This is the only way. And we have seen these by simply discussing the pre-processing stage of the music genre recognition. The other aspect is about, well, this device looks tiny. And at the very beginning of this talk, I present an MP3 player, which is a microcontroller, but it was already quite sophisticated also in terms of UI. This is because they are tiny, it's true, but they offer enough computational power and memory for many applications. The third aspect is the following. If TinyML is where it is now, is because of the incredible contribution from the open source community. And here I want, on behalf of the community, thank every contributor worldwide, because if this technology is evolving and is exactly where it is now and is enabling us to build fascinating applications, is only because of the open source community. So thanks everyone. I really hope you enjoyed this session.
Thank you so much, Gian Marco. It was a great presentation, and I see many questions, which are another sign of your great talk and how it has been well received. We have few minutes till the end, so let's try to address some of those. And then obviously you are kindly required to address the others so that in the forum there will be a record of them. So let me pick some. For example, do you touch other architectures like SP32 or else in the book?
Not the ESP32 in the book. These has been, in particular, as I said, the three platforms have been tested. So these are the platforms. I might consider exploring some of these in the future.
Okay, thank you. And does these supported boards have all the required capability, such as mic and speaker, or do a guy need to buy additional hardware like external mic or USB headphones or others?
So the boards proposed for this book are proposed to address different scenarios. If you want to have a board with the microphone, you can use directly the Arduino Nano 33 BLE Sense. If you want to have the full experience, also to learn how to connect the microphone, yeah, you need to buy it, as I presented today. And the Raspberry Pi Pico, in fact, is used to demonstrate or explain the other scenario where you need to connect different peripherals to the or different sensors to the board. So yes, you can with the Arduino Nano. If you want the full experience, you can use the Raspberry Pi Pico or the SparkFun Redboard Artemis Nano.
Thank you so much. Another is MFCC, mainly used in speech recognition. So essentially how the feature of speech and music genre relate, because these are different, there are different frequencies involved.
Okay, so the speech works also quite well for music genre. There is also temporal dependencies between these speech, and that is the reason, for instance, has been proposed LSTM, because in theory you can also use a convolution neural network, because what you obtain after this stage is something that resembles an image. However, let's say the pixels or the values returned by this feature extraction method, they also have a temporal dependencies. The temporal dependencies is due to the overlapping of the frames that you have when extracting the MFCC coefficients. And so that is the reason. So you can use it also for music genre. Remember, the hyperparameters play a crucial role. What is differs from music genre and speech recognition is actually behind the selection of the hyperparameters. For music genre, we expect more coefficients to grab more to have more details about the spectral content of the clip. For speech recognition, instead, this is not strictly required. What we want is actually the beginning of the utterance.
Thank you, Gian Marco. Another question, are there any good sound feature extracting techniques which does not use FFT, alternative approaches, others?
Okay, might be, as I said, I'm, from what I know, the MFCC is quite good. There are cases where actually this is integrated. No, integrated, I don't like to use integrated, but it's actually part of the learning problem is inside the model. However, the less sophisticated the feature extraction, the more complex, more computational power generally is needed for the machine learning model. So it's actually a trade-off. So it's true that this is actually more computationally expensive than other feature extraction methods, but at the same time, it helps us to keep the model quite small.
Thank you. Did you find any difficulties or limitation in the implementation of recurrent neural network in TensorFlow Lite Micro? Is it smooth as for CNR to deploy on microcontrollers?
Okay, very interesting question. Absolutely, I want to say that it was very, very simple. There is only one aspect you need to consider when you convert the TensorFlow model to TensorFlow Lite, because what you want here is to use the fuse LSTM and not the unrolled LSTM, because LSTM can be implemented in different ways. But the unrolled LSTM dispatches so many operators and can be quite inefficient. By using the fuse LSTM, you force in TensorFlow Lite to dispatch that operation, and it runs quite well. Also because it's inside the CMSIS-DSP library. So there is also, if you're using an ARM Cortex-M microcontroller, this will be also optimized for you.
And lots of Cortex-M do have float 32. Does it help to improve the accuracy?
Okay, I haven't seen any bad accuracy with FP32. The reason is quite simple, is because the integer fixed point arithmetic has been considered during training. Therefore, we have also minimized the risk of accuracy drop. The floating point, in particular, the floating point 32 is probably too much for this kind of scenario, and the quantization is certainly quite good and it does not require it. As I said, floating point is not strictly required for that.
Thank you, Gian Marco. I think we are running out of time. However, there are still many other questions pending. Let me also note that many people expressed their gratitude to you for your great presentation and all the topics that you covered. So this is a sign of great appreciation. Let me also remind that to the attendees that first of all, this conversation can continue on the forum page, and I encourage everyone to do so, as well as Gian Marco, please, to address the remaining questions. The slides and the video will be available on the YouTube channel very soon. So if you are not subscribed, please do so. And continue to follow up the meetups, the talks, and please register to the TinyML Summit as soon as possible, because it's going to be a great event. Then let me get the remote control, Gian Marco, so that I can just remind, thank you, just remind that TinyML talk of Gian Marco, as well as many others, are happening thanks to the great support of our TinyML strategic partners. The list is growing. This is a great sign of interest, support, and endorsement of all the activities that the TinyML community through the foundation are carrying. So let me remind also the executive strategic partners and the others one by one. Welcome, Cynthia. Then the platinum strategic partners, Embedded UR, Sony, the gold strategic partners, ARM, Edge Impulse, Infineon, Innatera, Renesas, ST Microelectronics, Synaptics, and the silver strategic partners, AIZ, Arduino, Brainchip, Efficient, Waves, Gravity, IMAX, ImageBot, Not AI, NXP, PNG, PME, Poly Technology, Corvo, Schneider Electric, Sensing, Silicon Labs, and TDQ. So thanks a lot, Gian Marco, for the time you devoted in preparing and explaining today. This is a very interesting tool. I think people is looking to the link of the book in order to buy it as well. So please do share it so that people can easily find it. Thanks again. Thanks to Olga and Evgeny, as usual. And let's meet to the next episode of the TinyML. Bye.